So we'll start in 2 minutes.
I think we can start.
Can we start? Okay.
Next
Okay.
speaker have 2 minutes more time.
Yeah, we will. So I'm starting now. Okay.
Yeah,
So before announcing our first speaker today, let me just make my simple introductions. First of all, I would like to say it is my great pleasure. Can you hear me?
yes.
Okay.
Yes, we can hear you.
Okay, good. It's my great pleasure and honor to say welcome all of you to this exciting sessions of Fourth International Conference on Holography and its applications. So today in this afternoon session, we have three distinguished speakers whose works lies at the heart of the modern theoretical physics. So before starting introducing our first speaker, I would like to remind our speaker, each speaker will have 40 minutes for talk and 5 minutes for the Q&A session. Okay, so our first speaker today, I cannot see her details on my screen, but I will try to read from on the paper. So our first speaker is Christina Rugina. She's going to present the modular Dirac equation and cryptography. Okay, please take your action, and now it's your turn. Thank you.
Thank you very much, Professor Dormes. Hi, everybody. I'm really delighted to be here, invited to this wonderful conference. It's a pleasure and an honor to be with you here today at Khazar University. And I must say, as a preamble, that my neighborhood where I live in Bucharest has a strong connection with the Azerbaijani people, Azeri people. We have a park here in our neighborhood, which is a friendship park between Bucharest and Baku. And in the park, there is a statue of late President Haidar Aliyev. And I must say, I'm fond of the Azeri culture too. I like Fikret Amirov and Khan Mamadov and Garagarayev, some of my favorite classical composers. And whenever I stroll through that wonderful park of friendship here nearby, which is within 100 meters from where I live, I always ask, well, it's very nice that we have a President Haidar Aliyev statue here, but why don't we have some statues of Fikret Amirov and Garagarayev too? So anyway, that's the preamble, and I can now start on the talk. And please let me know if you see the shared screen.
Now we cannot see anything.
Do you see? Do you see the slides?
No.
No, you don't.
Yes, we see.
You do see it now?
Okay. It's just appeared in my another screen. I'm sorry.
Yeah, okay. So you can see the slides. Okay, so we can start. The talk is about the modular Dirac equation and some skeletons of a future paper which will relate the modular Dirac operator to cryptography. And it's based on work, as you see, published actually in General Relativity and Gravitation paper published in 2022. And now I'm working on another paper, which I'm trying to present here, the skeleton, as I said, of that new paper. And as you can see, I'm from University of Bucharest and also from the Canadian Quantum Research Center. So in principle, we place this work in the larger context of the black hole information paradox. And there has been a lot of work to do black hole interior reconstruction. The framework in which this work is placed is entanglement wedge reconstruction. We will see towards the end of the talk that actually, because there is modular flow on the boundary, the causal wedge actually coincides with the entanglement wedge. The entanglement wedge is that region of the bulk that is delimited by the famous Ryuta-Kayanagi surface. And the causal wedge is the past and future domain of dependence of the boundary. So in principle, points in the bulk that can be reached causally. And the entanglement wedge usually contains the causal wedge, and it generally does not coincide, is larger than the causal wedge. But we will see how they actually, via a theorem by Engelhardt and others, that the two causal and entanglement wedges coincide in our case. So, of course, everybody knows about the information paradox and the fact that we are trying to decode the Hawking radiation, and that's possible, especially after the page time. There are wonderful talks about the page curve in this conference, so you can refer to those talks in understanding more about the page curve, which is not really the topic of the talk. What can I tell you? A little bit about the pre-existent work, which will be about 20 slides out of the 33 on the published paper on the modular Dirac equation. What was the aim of that paper is to see and actively reconstruct a bulk spin 1/2 particle at the center of the ADS2 spacetime with an equation, the modular Dirac equation, that gives the evolution of this bulk spin connected via a wormhole in the embedding spacetime to the boundary. So even the modular Dirac equation predicts the fact that we can reconstruct spin 1/2 of fermion in the middle of the bulk, ADS2, nearly ADS2. So the new paper I'm engaged in presents a novel context and connection with Ramanujan's work, which can become the generator of a Jacobi mock modular form. There will be plenty of definitions about modular forms and Jacobi modular forms and Jacobi mock modular forms and mock modular forms later on. So don't worry if you don't understand the terminology at this point. What is to be remembered at this point about the Jacobi mock modular form is that it counts the degeneracy of the fermionic black hole microstates. And there has been work by Dabholkar and collaborators in a seminal paper from 2012 presenting how Jacobi mock modular forms count the degeneracy of the bosonic black hole microstates. Here we extended to fermionic black hole microstates. We seek a cryptographic key. It's perhaps a misnomer in the talk here, the cryptographic key, because people probably expect ample references to quantum cryptography and things, which is not the case here in this paper. What we will try to do in the paper which I'm going to complete, is to set up a connection between a notion of cryptographic key and the space-time mutual information. We will see a little bit of the setup later in the talk. And the fact that this cryptographic key, which is the maximized space-time mutual information, depends in a subtle way on the Jacobi modular form, which again counts the degeneracy of the fermionic black hole microstates, and the nearly ADS2 charges, which were found by Lin, Maldacena, and Zhao. So that's the plan of the talk, basically. And now let's introduce our friend, the modular Dirac equation. The equation looks weird, perhaps, at first. And it looks like that, as you can see in relation 1. But it really has a lot of connection, backwards compatibility with the thermofield double state, and with regenesis by Professor Hong Liu, work by Professor Hong Liu, and the correlator involving the Dirac operator, modular Dirac operator, also has connection with the 2019 paper by Maldacena, Lin, and Zhao. So anyway, there is a connection between the modular Dirac operator, and we'll see how that looks in ADS2 space-time. It is a connection with non-commutative quantum mechanics with Cohn's cocycles, which is defined as in relation 4. So a non-commutative geometry. And I can say that actually we will see how the modular Dirac operator is related to Tomita Takesaki constructions, which are generically bipartite Tomita Takesaki, and the modular Dirac equation is multipartite entanglement representative. In any case, the relative modular operator introduced by Levin, Shabazi, Moghadam, and Sony in 2020 looks like that, where rho is the density matrix associated to algebras associated with the region A of the space-time. It's also like in Tomita Takesaki construction, A prime is a commutant of A. And, just to form a little bit of intuition, when you have two algebras associated with a region of space-time, that actually indicates it can describe, Tomita Takesaki doesn't describe only black holes, two-sided black holes with a left and a right sides. It also describes things that are bipartite in entanglement, like for instance in quantum mechanics, it can describe the preselection and post-selected states in quantum mechanics. That can be described by Tomita Takesaki as well. So they have a very it's a mathematical formalism, but they have a very firm ground in quantum mechanics and black holes. So the applicability of Tomita Takesaki construction goes into black holes and quantum mechanics. So whenever you have, because you have an algebra and a commutant, which is a commutant of a larger algebra, it's always sort of a bipartite thing. So when you have a bipartite entanglement, chances are that the Tomita Takesaki construction can apply. Then we move on to the ADS2 metric in those coordinates, as you see. And in these coordinates, the Dirac operator is written, that formidable expression is something manageable like that. I mean, with the power of 1 plus is, so complex number, where S is from concocycles, the modular time. So that would be the significance of this S, the modular time on the boundary. And you can write because delta, the Dirac operator is bounded, it can be written like that, and it can be proven that there is, when you expand the Dirac operator, it goes into the Schwarzian derivative. So that's an indication, another indication that we are talking about quantum gravity here. The fact that we retrieve the Schwarzian derivative. And it has connections, deep connections with Schwarzian theory. Then the modular Lagrangian from which the modular Dirac equation is derived looks like this. And this, I can anticipate a little bit that slide, a theory of Dirac operator raised at complex powers, developed by L. Bode. We'll reach that slide immediately. And so the raising of the Dirac operator at this power is somewhat understood by mathematicians. And it implies a Guillemin algebra and other things. So it's a problem that has been studied by mathematicians. Now, why does our equation, which is an equation of propagation of a spin 1/2 from the middle of the bulk to the boundary, why does it look like that? Why the propagating equation looks the way it looks? In terms of left and right operators, the thermofield double state correlator looks like this. There is a similar expression derived by Lin, Maldacena, and Zhao in 2019 also. And that's the correlator for the thermofield double state, and also the correlator for various types of left and right, what can I say? I mean, these are operators acting on the left side of the black hole, and these are operators acting on the right side of the black hole. So this paradigm of a two-sided black hole is a left and a right side, and the propagator looks like this. Our propagator equation with a potential, let's say, from the Lagrangian, which looks like that in expansion, gives in the first degree approximation where x minus 1 is the embedding coordinate for ADS2 in ADS3. So as you know, there is an embedding, and x minus 1 is that third coordinate. And so that's how we can write the propagator. And if we compare our result with Gao and Yu, and also Lin, Maldacena, and Zhao, we see they are proportional. So it's an approximation. It's a deep thing here. The fact that there is more to ADS2 from the fermionic perspective than what it is generally derived for the bosonic case. It's, in my opinion, a deep thing that ADS2 behaves this way with the Dirac modular operator at the fermionic level, spin 1/2 basically. And so given these coordinations with Gao and Liu and with Maldacena and collaborators, we have the inkling that the Dirac equation is probably correct. You know, that's what the referees of the paper believed too, since they published it. So it was not only my personal opinion. Now, the solution of the modular Dirac equation was mostly derived by L-Bode. So I'm just here adapting a little bit with my initial conditions and the fact that the modular Dirac equation contains a mass term and that's a family of concocycle spinors is the solution in modular time S. So adapting a little bit and the fact that the power of the operator is 1 plus IS, where E mu is this function in Eigenbauer polynomials and hypergeometric functions. So this is work done by L-Bode in 2004. And our solution, as I said, has a well-posed initial value problem in conformity with L-Bode, and this normalization is realized on a unit hyperbolic ball. And our hyperbolic solution gives a sense in which the evolution of a bulk spin in ADS2 is known with a certain degree of approximation, even in the case of unknown couplings. So even if we didn't know the couplings, we'd still know the evolution of the bulk spin at the center of the bulk with this equation. Then the hidden modular symmetries are constructed in analogy with hidden symmetries of type Killingiano, conformal Killingiano and Killingiano, and has similar equations, except the operators are raised at this complex power. And we get modular closed conformal Killing vectors for which the only not null components are these, and that's the solution. A lot of symmetry, hidden symmetries, modular symmetries of ADS too. I must say that nearly ADS2 space-time has been studied thoroughly in terms of charges and generators by Maldacena, Lin, and Zhao. And so we add to that work these hidden symmetries. And Dirac type modular operators in analogy with Dirac type operators for the regular Dirac operator. And they look like that, very similar to the Dirac operator, except we raise to the power of 1 plus IS. This relation holds, the unit roots have this relation, and the Dirac type operator follows this rule with the Dirac operator. Now, going to the generalized Tomitaka-Kisaki construction I hinted at in the beginning of the talk is this. So the regular Tomitaka-Kisaki construction is basically this, adapted, of course, to our operator, the modular Dirac operator, but this is the modular operator. This is the usual antilinear operator, and J is related to S. So the omega is the Fourier transform of the modular Dirac equation and appears in the regular Tomitaka-Kisaki construction like that. So, of course, since we are studying black holes, no wonder we can adapt the Tomitaka-Kisaki construction to our needs, to this Dirac operator raised at a complex power. where we go into is the fact that we have an infinite dimensional algebra of type von Neumann 1 infinity, like that. In regular Tomitaka-Kiyosaki construction, there exists one large algebra and one commutant, as I said, so a bipartite thing. Here, in a generalized sense, there exists an infinity of commutant algebras of type 1 generalized von Neumann as follows. I don't have a slide for von Neumann algebras, but if you're interested in finding out more about von Neumann algebras, I can direct you to some information regarding that. The generalized, again, Tomitaka-Kiyosaki construction, since we are talking in the case of the Dirac operator of multipartite entanglement, we can write a multiverse wave function like that, where these are regular creation and annihilation operators, like a regular, only is raised to this power, this complex power. And that we claim is the wave function of a multiverse. Multipartite entanglement in the sense of replica wormholes. Relative entropy between bulk and boundary, that is in total analogy with the Araki entropy. In the Araki entropy, introduced by many people, including Witten, Professor Witten in 2018, in a paper in 2018, the Araki entropy, relative entropy, here instead of our modular Dirac operator, it's the modular operator in the and it's basically, let me backtrack a little bit so that you understand. It's basically this operator delta in the Araki definition. And so we generalize to our case the Araki construction to the modular Dirac operator. What we see in this relative entropy is that the second law of thermodynamics holds in total analogy with the Araki entropy. In that case, the operator is also a complex operator. And so this complex entropy obeys the complexified version of the second law of thermodynamics, much like the replica wormhole saddles. So what I can say about this complexified version is that the real part of the entropy, it really obeys the regular second law of thermodynamics. And so you complexify the entropy by analytic continuation if you want, but the real part obeys the regular second law of thermodynamics. And it's been proven for the Araki entropy, and we have some form of proof in the paper also. The effect of unknown couplings on the current model, we have compatibility with a paper by Almeri and Lin from 2021 to investigate the effect of unknown couplings K on the power of bulk reconstruction of the current model. So we start with this matter action in analogy with Almeri and Lin, and we get this similar result from here to here in a first degree approximation of the expansion of the modular Dirac operator. Remember, there's a Schwarzian in the expansion of the logarithm. So we get this compatibility with Almeri and Lin's work. We will see in the end that here for the paper we published in 2022, The conclusion was this means that we can't fully reconstruct the bulk in the case of unknown couplings. We can do that only in the first degree approximation of the Dirac modular operator. We will see that with new insights from 2022 and 2024, we can actually conclude that the couplings are always known for nearly ADS2 spacetime. Now, let's turn to the second part of the talk, it's the new paper that I'm writing, and it relates to cryptography and modular Dirac equation. So I presented things about modular Dirac equation so that you understand the current paper, which is in writing. So I'm practically in the incipient stages with a paper, but I wanted to present the ideas mostly of the paper because I thought they were quite interesting, and there will be some progress in this direction, you'll see. So we will found our own Jacobi Mach modular form generated by the modular Dirac operator. You'll see the slides in a moment. And this represents the fermionic degeneracy in a black hole in nearly ADS2, the geometry of the throat of higher dimensional black holes. We will introduce the notion of space-time mutual information, which was introduced previously by a number of authors. And we will see that it depends on the ADS2 charges and the fermionic degeneracy. We will introduce how space-time mutual information becomes a cryptographic key when it represents maximal entanglement, which translates into a problem of finding a maximum with a constraint, given that the ancilla system is represented by the generalized BMS symmetries. Now, this might sound a little confusing if you don't have the background in these directions. But things will become a little more clear, I hope, clearer in a moment. So in order to understand the connection with Ramanujan's work, we had to dig out a few definitions for the people who don't have background in modular forms. And there is a nice paper by Doublecar and Putrov from 2021, which is a very mild introductory paper for beginners into this subject initiated by Ramanujan. So the definition of modular forms first. If we consider H to be the upper half plane, a modular form of weight K on SL2Z is a holomorphic function that transforms like relation 35. For any matrix ABCD with the elements ABCD in SL2Z, and for an even integer K, and it is bounded as imaginary of tau goes to infinity. So that's the definition of modular form. Then their definitions are hard to remember and understand if you don't have the background, but at least you go a little bit through it so that you understand where we are trying to take our paper, into what direction we are trying to take our paper. So phi is defined on H times C, and that's the definition of Jacobi modular forms, or simply Jacobi forms. So there are functions phi of tau and z. Now there are two parameters, and it is modular in tau and elliptic in z, which means that the modularity is relation 36, and the fact that it is elliptic is relation 37, so based in z. So that's the Jacobi modular form. Now, definition of Mach modular forms, things get a little more complicated, more and more complicated with the definitions. So the Mach modular form of weight K, H is a holomorphic function in H with at most exponential growth, which is not quite modular. So H is holomorphic but not modular. That's why Mach modular. The function G is called the shadow and the sum is called the completion of H, and it is modular but not holomorphic. So we have an interplay of we have in modular forms certain objects are holomorphic but not modular, and the completion is modular but not quite holomorphic because G star is non-holomorphic, and obeys this equation 38, where a G bar, sorry, this it was supposed to be a long bar, is the conjugate of G, where G is the shadow, and it's a modular form. But this is not holomorphic, so the non-holomorphicity is gathered in G star because H is holomorphic. So H hat is modular but not holomorphic, and tau 2 is imaginary of tau. So that's modular. Now, what we are interested in are actually the Jacobi modular forms. And we introduce here the definition of a Jacobi modular Jacobi form of weight k and index m. It's a holomorphic function that satisfies the elliptic transformation property, just like in the case of the Jacobi forms, and has this Fourier expansion. It has the Fourier expansion also in the case of Jacobi forms, and the periodicity property also. I didn't write it so that I don't clutter the presentation, but in any case, these things are also properties of the Jacobi forms. And the thing here, the punchline, is that it obeys this expansion, where now there's an expansion in theta functions also for the Jacobi form. Only here, HLZ are modular forms, the coefficients. In the other case, there were just modular forms. These are Mach modulars. So in our work, we are trying to find a Jacobi Mach modular form like this, so with an expansion like that in Mach modular forms and theta functions, such that let me go here, such that there exists an operator associated with a theta expansion, which in our case is the modular Dirac operator. For the Jacobi forms, the operator is the heat operator, is the associated operator with a theta expansion for the Jacobi forms. But for us, we are looking for the modular Dirac operator associated with a Mach modular Jacobi form. So it was previously worked on the partition function for bosonic microstates of immortal black holes, was also a Mach modular form, and a work, seminal work of 150 pages of paper by Doublecar and collaborators. So that's a mammoth paper, and very interesting. What is for the Mach modular, going back to definition, remember there was a modular condition. This is not phi, the Mach modular function, but the hat, f hat, obeys the modular expression. So which is the completion? Remember, this is the completion with Mach modular forms in the theta expansion. So perhaps that's too much detail at this point for people who don't have background. But I had to go through these definitions to understand what my goal is in terms of my paper, to find for fermionic microstates, Mach modular form that describes the degeneracies. Okay. Now we move on to space-time mutual information. We know the mutual information for two regions that are basically spatially separated is like that, where S is the entropy, and that's the joint entropy. The relative entropy of two regions has this formula, which is the first region is characterized by rho density matrix, and the second by sigma, and that's the relative entropy. The space-time mutual entropy for two causally connected regions, like in our case A and B, with an ancilla system W, so a third system, which is an ancilla, which in our case is the future null infinity region, is given. So this space-time mutual entropy is given by this relation, where this is entropy, and these are various types of densities, which we will discuss immediately. So this is another very important quantity, and I forgot to quote here, I apologize, the paper. And if I go to the paper, I have it open here, I think, to give you authors. I apologize for this fact that I missed. It's the paper is called Space-Time Generalization of Mutual Information by Glorioso, Chi, and Young. So that's the paper, which I forgot to cite here. This space-time mutual information is taken from that paper. This definition, V is the system ancilla coupling. For two spatially separated regions, the regular mutual information is given by the relative. It's an alternative definition of mutual information. The relative entropy between the connected and disconnected parts. So when you're talking about spatially separated regions, your mind can immediately go to side A, left A, and side right B of a black hole. That's a typical spatially separated region example. But in our case, rho BW is the density matrix of the connected state between B is the boundary, and W is the ancilla at infinity, future infinity, and rho B0 represents the unperturbed evolved state in B. And this is analogous to the disconnected state in this state in mutual information. So that's just an introduction of the space-time. That's a new paper, I think, from 2024 with a space-time mutual information. And now the density matrices, which represent, in our case, the density matrices of regions around the center of the bulk, including regions of the horizon, respectively the corresponding region of the boundary. So rho A and rho B. Rho B is the boundary, rho A is the region around the center of the bulk. And W is the ancilla system.
I'm sorry.
Yeah.
So time is over. Please, can you just
Yeah,
summarize?
I'll just let me finish this slide, which is important.
Sorry for it. Yep.
Just let me finish this slide, which gives you all the information about the projected paper. These density matrices depend on a subtle way of the nearly ADS2 symmetries uncovered by Maldacena and collaborators, and the fermionic black hole partition function, the Jacobi-Mach modular form, which we tried to find. J1 acts as a cryptographic key, allowing the boundary observer to see behind the horizon when it is associated with a maximal entanglement between regions A and B, which is a problem of determining the maximal space-time mutual information with a constraint given by ancilla W. there is one more slide, if you allow me. The whole nearly ADS2 can be known and computed. It was proven by Engelhardt and collaborators that when there is a modular flow, like in our case on the boundary region, its entanglement wedge equals the causal wedge. If that's true, then because there is in this paper, they proved that the causal wedge can be completely computed on a quantum computer. It follows that nearly ADS2 space-time can be completely known. This is equivalent to saying that all couplings are known for ADS2. And the conclusions are repeats of what we saw, and I end here. Thank you very much.
Thank you very much for Ms. Rugina for detailed and illuminating talk. Thank you very much again. So if you have questions, so now we can take it. Is there anybody here has a question? No? I think
maybe I have one.
Okay, go ahead, please.
Short one, yeah. Thank you, Prof. Rugina, for your very nice talk. My question and my maybe concerns is about the solving, for instance, Dirac equations in the presence of gravity. It is not a simple task, as you know, and so if you want to compare your results with origin Dirac solutions in, for instance, in ADS or in the presence of in the close-up gravity, like a black hole or so. So how we can compute and how we can compare the results? Because
right. There is, I understand. I mean, those questions, those concerns were addressed in, modified Dirac operators work. There's extensive work, and part of my PhD thesis was related to that too. Getting the Dirac operator to be modified to take into account gravity and consequently withstand quantum gravity. And there's a lot of work by Chi, by Professor Yasui, by Kubiznak, by
no, I mean no. We don't worry about quantum gravity. We just want to consider gravity as a ball, as a background, classical background, and we spread, for example, a fermionic field in the presence of gravity. So how we can deal with fields?
Well, this is the connection of the modular Dirac operator and quantum gravity is given by the presence of the Schwarzian term in its expansion. Yes. Which is a trace of quantum gravity. So we have taken into the expansion of the operator into account quantum gravity. It's a quantum gravity effect, the Dirac modular operator. And what can I say? You can email me privately if you want, and we can discuss, because I think our time is up.
Yeah, sure.
Thank you very much.
I'm next speaker.
Yeah. Okay. So thank you very much again, Ms. Rugina. And now I will introduce